Something changed on the night of February 24th, 2026. Not on Earth. Not in a lab. In the sky above Chile, a machine opened its eye. And in a single night, it found 800,000 things that humanity had never seen before. Not discovered over years. Not cataloged over decades. 800,000 in one night. Scientists did not celebrate quietly. They described it as the beginning of something they could not fully prepare for. Because when you build a machine powerful enough to see everything, eventually you see something that changes everything. This is that story. There's a mountain in Chile called Cerro Pachón, and on its summit sits something that most people on Earth have never heard of. It does not look like the telescopes in movies. It does not have a dramatic backstory built on a single eccentric genius. It was built by thousands of people over more than 2 decades, funded by both the National Science Foundation and the U.S. Department of Energy, and quietly commissioned over several years, while the world was distracted by other things. It cost $800 million. It houses the largest digital camera ever constructed by human hands. And on the 30th of June, 2026, it officially began doing the one thing it was built to do: watch. Every patch of sky, every night, for 10 years, without stopping. This is the Vera C. Rubin Observatory. And what it has already found in just the first weeks of operation is not what anyone expected to find this soon. Think about what that means for a moment. We are not talking about a telescope that occasionally points at something interesting. We are not talking about a machine that waits for astronomers to decide what to look at. The Rubin Observatory does not work that way. Every 40 seconds, its camera captures a new image covering 6 square degrees of sky. That is roughly 45 times the surface area of a full moon in a single shot. It does this all night, every night. Then it sends that data on a seconds-long journey from the Andes Mountains to a processing facility at SLAC National Accelerator Laboratory in California, where automated systems begin comparing every new image to a reference image of the same region, pixel by pixel, change by change. And every single time something has moved, brightened, dimmed, or appeared where nothing appeared before, the system fires an alert within 60 seconds, automatically, to scientists around the world. On its very first night of real scientific operation, it fired 800,000 of those alerts in a single night. But here's where it gets strange. Scientists had spent years preparing for this. They had run simulations. They had modeled the data. They had built the software to handle what they thought was coming. And still, when the machine turned on and began doing what it was designed to do, what came back from the sky was more than expected, more complex than modeled, and in some cases, pointing toward things that should not exist according to our current understanding of the universe. This is not a story about a telescope. This is a story about what happens when humanity finally builds a machine powerful enough to see what the universe has been hiding. To understand the weight of what the Rubin Observatory is doing, you first need to understand the woman it was named after. Vera Rubin was an American astronomer who spent much of her career doing something that nobody took seriously at the time. She studied how galaxies rotate. In the 1970s, working alongside her colleague Kent Ford, she discovered something that should have been impossible according to everything physics said at the time. Stars at the outer edges of galaxies were not slowing down the way they should. Based on the visible matter in those galaxies, the stars, the gas, the dust, the outer regions should be moving slower, following the same rules that govern our own solar system. But they weren't. They were moving just as fast as stars near the center, sometimes faster. And there was only one explanation that made any physical sense. There had to be something out there that wasn't visible, something massive enough to hold those stars in their orbits, something that did not emit light, did not reflect light, did not interact with light at all, something that was there without being there. She called it what she saw in the data, invisible matter. The scientific community would eventually call it dark matter. What Rubin discovered in those measurements was not a footnote in physics. It was a revolution. It meant that the universe we can see, every star, every planet, every galaxy, every nebula, everything that has ever been photographed or mapped or cataloged by every telescope ever built, represents only a small fraction of what actually exists. According to current estimates, the matter we can see makes up roughly 5% of the total energy content of the universe. Dark matter accounts for approximately 27%. And the remaining 68%? That is dark energy, a force so strange and so poorly understood that physicists describe it as a kind of pressure built into the fabric of space itself, pushing galaxies apart at an accelerating rate. The universe is not just expanding. It is expanding faster and faster in a way that has no clean explanation within our existing models. This is the problem the Vera C. Rubin Observatory was built to confront, not to study casually, not to observe from a distance, to attack directly with the most powerful optical survey instrument ever constructed, for 10 years straight, until either the mystery yields or the mystery deepens into something even more unsettling. And it has already found things that are making physicists nervous. Here is what most people are not seeing in the headlines about the Rubin Observatory. The conversation in the scientific community right now is not just about what the telescope is discovering. It is about what another instrument, the dark energy spectroscopic instrument known as DESI, has already found, and what it means for everything we thought we knew. DESI completed its planned sky survey in April 2026 after mapping galaxies at a pace faster than anyone had anticipated. Its results, accumulated over years of observation, have produced something deeply uncomfortable for cosmologists. The data hints, not proves, but hints with increasing statistical weight, that dark energy may not be what Einstein proposed it to be. Einstein's model of dark energy treated it as a cosmological constant, a fixed value baked into the equations of space-time, unchanging across time and across the history of the universe. But DESI's measurements suggest it may have weakened over cosmic time, that it may have been stronger in the early universe and may be fading now. And if that is true, it does not just refine our model of cosmology, it breaks it, fundamentally. Because a changing dark energy requires physics that does not yet exist in any of our current theories. This is where the Rubin Observatory enters the picture in a way that is far more consequential than most news articles are. Explaining, the primary cosmological mission of the LSST, the legacy survey of space and time that officially began on June 30th, 2026, is to perform what astronomers call weak gravitational lensing. This is the technique of looking at the shapes of billions of background galaxies and measuring how those shapes have been subtly distorted by the gravitational influence of matter between us and them. Dark matter does not emit light, but it bends it. By precisely cataloging how billions of galaxy shapes have been warped and twisted by invisible foreground mass, Rubin can build the most detailed three-dimensional map of the universe's mass distribution ever assembled. And from that map, cosmologists can extract the precise fingerprint of dark energy, how it has behaved over cosmic time, whether it has changed, and whether Einstein's constant was actually constant at all. According to the scientists running Rubin's commissioning, after just 1 year of full LSST data, their weak gravitational lensing measurements are expected to reach a precision comparable to everything DESI achieved over its entire survey. This is not an upgrade to our knowledge. This is a confrontation with it. And here is where it gets worse. The tension in cosmology is not limited to dark energy. There is another crisis, one that has been building for years, and reached what physicists describe as a 5 sigma level of confidence, meaning it is almost certainly not a statistical fluke. It involves the Hubble constant, the number that describes how fast the universe is expanding. There are 2 primary ways to measure this number. One looks at the very early universe using the cosmic microwave background, the afterglow of the Big Bang, and calculates what the expansion rate should be today based on standard cosmological models. The other measures it directly using nearby supernovae and calibrated distance markers in the present-day universe. These 2 methods give different answers, not slightly different. Meaningfully, stubbornly, persistently different, by an amount that cannot be explained by measurement error alone. Physicists call this the Hubble tension, and it sits at the heart of everything wrong with our current cosmological model. What most people are not seeing is that the Rubin Observatory was designed to help resolve this tension, and it may instead make it worse. Because when a machine this powerful begins measuring the universe with this level of precision, it does not smooth over inconsistencies. It exposes them. Every calibration error, every assumption baked into existing models, every simplification that seemed acceptable when data was sparse, all of it gets pressure tested against a flood of new measurements, and the flood has already begun. Consider the scale of what is happening right now in real time. Each night, the Rubin Observatory's camera captures thousands of images. The data, approximately 10 terabytes every single night, flows from Chile to California in near real time, where it is processed and compared against previous observations. The system generates up to 7 million alerts per night, each one flagging something that changed in the sky since the last time Rubin looked. 7 million per night. Every alert represents a supernova, an asteroid, a variable star, an active galactic nucleus, a gravitational microlensing event, or something that the automated systems cannot yet classify. Astronomers around the world receive these alerts and begin coordinating follow-up observations using other telescopes. The result is a distributed, real-time global observatory unlike anything that has ever existed before. And in just 6 weeks of pre-survey optimization, before the full LSST even officially began, the telescope had already discovered over 11,000 previously unknown asteroids. Among those were 33 near-Earth objects and 380 trans-Neptunian objects, icy bodies orbiting beyond Neptune whose distribution in space holds records of how the outer solar system formed and evolved billions of years ago. Think about what that number represents. Previous surveys, operating over years with far less capable instruments, had built up catalogs of these outer solar system objects over decades. Rubin found 380 of them in 6 weeks. When the full 10-year survey is complete, the number of known trans-Neptunian objects is expected to increase by an order of magnitude. And what those objects reveal about the early solar system, and potentially about things we are not yet looking for, is something that cannot be fully predicted. What most people are not seeing is this. Among the scientific community, the conversation about Planet 9 has reignited. Planet 9 is a hypothesized massive object, estimated to be 5 to 10 times the mass of Earth, that may be orbiting in the deep outer solar system, far beyond the Kuiper Belt, in a region so distant and dark that no telescope has yet been able to directly image it. The evidence for its existence is indirect but persistent. A cluster of trans-Neptunian objects with orbital parameters that are statistically improbable unless something massive is gravitationally hurting them from a great distance. Planetary scientists like Mike Brown at Caltech have spent years building this case. And now, Rubin is finally powerful enough to either find it or definitively rule it out. According to informed sources in the planetary science community, this is one of the most anticipated outcomes of the entire LSST mission. If Rubin detects Planet 9 directly, it rewrites the map of our own solar system in a way that no discovery since Pluto has managed. If it finds more objects with warped orbits but no planet, that is also a result, one that demands an explanation, and that may point toward something stranger than a missing planet. But here's where the story gets even more complex. The Rubin Observatory was not built to answer one question. It was built to answer all of them simultaneously. And this creates a scientific situation that has never existed before. In the history of astronomy, major discoveries have tended to arrive in sequence. One telescope opens a window, scientists peer through it, build theories, then build a new telescope to test those theories. The process is deliberate and slow. Rubin has collapsed that process. It is observing supernovae, dark matter, near-Earth asteroids, trans-Neptunian objects, gravitational lensing, active galactic nuclei, stellar variability, interstellar objects, and the large-scale structure of the universe, all at the same time every night for 10 years. The volume of discovery happening simultaneously is so large that no individual scientist, no single institution, can process it alone. This is why the observatory's alert system was built to be public from day one. When Rubin detects something, the world detects it. Researchers at universities with limited resources can access the same real-time data stream as teams at MIT or Caltech. This is a democratization of the universe, and it means that the discoveries coming from Rubin over the next decade will arrive from places and people that the scientific establishment has not anticipated. Now consider what happened on February 24th, 2026, in that first night of scientific operation. Among the 800,000 alerts that went out to scientists around the world were the flares of new supernovae, the flickers of stars with active black holes at their cores, and the movements of asteroids cruising through our solar system. But among those alerts were also things that the automated classification systems flagged as uncertain, objects that did not cleanly fit into known categories. Transients without clear signatures, point sources that appeared and then faded in ways that did not match standard models of stellar variability or known types of explosions. Scientists in the community who have been working with Rubin's commissioning data have described this in careful, measured language, but the underlying message is clear. The sky is doing things that the models did not predict. And when the sky does things that the models did not predict, there are two possible explanations. Either the models are slightly wrong, which is fine, models get refined, or the models are missing something fundamental, which is not fine at all. That would mean there are physical processes operating in the universe that have left no trace in any of the data we have collected over the entire history of astronomical observation until now. This is the threshold the Vera C. Rubin Observatory is standing at, and it is only 2 weeks into its 10-year mission. Here's the broader context that makes all of this feel urgent. We are living through a convergence of cosmic survey instruments that is unprecedented in the history of science. The DESI instrument finished its survey and is already pointing toward cracks in standard cosmology. The Euclid Space Telescope, launched by the European Space Agency in 2023, has begun releasing early cosmological data from orbit. The Nancy Grace Roman Space Telescope, NASA's next flagship space observatory, is scheduled for launch on August 30th, 2026, and will push the frontier of dark energy constraints into redshifts higher than anything Rubin or DAISY can reach from the ground. These instruments are not competing, they are triangulating. Each one measures the universe from a different angle, at different wavelengths, at different depths. And when they all agree, that agreement is powerful confirmation of what we know. But when they disagree, when the measurements from one instrument cannot be reconciled with the measurements from another, that disagreement is a signal, not of error, of discovery, of something the universe is trying to tell us that our current models cannot hear. The Hubble tension is one such disagreement. The potential evolution of dark energy flagged by DESI is another. The anomalies in the large-scale structure of the universe, where the distribution of matter at the largest scales does not perfectly match what the standard cosmological model predicts, are a third. These tensions are not new. Scientists have known about them for years. What is new is that we now have, for the first time, instruments powerful enough to either confirm them with overwhelming precision or resolve them by finding the hidden variable we have been missing. The real story here is about what happens to human knowledge when the resolution of our instruments finally catches up to the complexity of the universe. For decades, we've been working with maps drawn at low resolution, maps that were good enough to build theories on, but not detailed enough to see the cracks in those theories. Rubin is a high-resolution instrument, and high-resolution maps reveal things that low-resolution maps erase. Every ridge, every valley, every inconsistency that was smoothed over in the data begins to emerge. This is why the scientific community is simultaneously excited and anxious about what Rubin will find. It will not just add data to existing theories, it will test them in ways they have never been tested before. Consider the supernovae. The Rubin Observatory is expected to detect more Type Ia supernovae in its first few months of operation than were used in the original 1998 discovery of dark energy, the discovery that won the Nobel Prize and established the accelerating expansion of the universe as scientific fact. Type Ia supernovae are the standard candles of cosmology, explosions of a predictable brightness that can be used to measure cosmic distances with extraordinary precision. The more of them you can observe and the more precisely you can measure them, the tighter your constraints on dark energy. Rubin will observe millions of them over 10 years, and if those millions of measurements confirm DESI's hints that dark energy is weakening over time, then what was first suspected becomes what is established, and what is established demands explanation. And no explanation currently exists within the standard model of cosmology that can account for a dark energy that changes. This is not a small problem. A changing dark energy would require a fundamental revision of our understanding of what the universe is made of and how it behaves at its largest scales. It might require entirely new physics. It might require revisiting assumptions that go all the way back to Einstein. It might, and this is what keeps cosmologists awake, require us to accept that the universe is doing something that our mathematics has never described and that our intuition cannot yet follow. And this is where everything changes, because the Vera C. Rubin Observatory is not waiting for permission to find these things. It is already finding them. Every night, 10 terabytes of new data flows down from those dark Chilean skies into processing systems that compare today's universe to yesterday's universe, pixel by pixel. Every night, millions of alerts go out to scientists who are already at their computers, already loading data, already designing follow-up observations. The machine is running, the movie of the cosmos is being filmed, and what appears in the next frame is unknown, not because we lack the technology to capture it, but because what we are seeing is genuinely, provably new. Think about what that means for a moment. In the entire history of civilization, the universe above us has been a mystery that revealed itself slowly, reluctantly in pieces. We mapped the stars with the naked eye for millennia before we built the first telescope. We built larger telescopes over centuries before we realized galaxies existed beyond our own. We launched telescopes into space before we discovered that the expansion of the universe was accelerating, that dark energy was real, that most of what exists cannot be seen. Every step was hard. Every revelation required decades of patience and argument and failed hypotheses before the truth came clear. And now, for the first time, we have a machine that does not require us to choose what to look at. It looks at everything, and it compares everything. And every night, it finds something new and fires an alert, and somewhere in the world, a scientist opens their laptop and begins to understand what was just revealed. The Rubin Observatory's final data set, when the 10-year LSST survey concludes in the mid-2030s, is expected to contain billions of objects with trillions of individual measurements. The total archive will run to approximately 500 petabytes. That is 500 million gigabytes. No human being will ever directly examine most of it. The discoveries hidden inside that archive will be found by machine learning systems, by AI algorithms trained to recognize patterns that no human eye could detect, by automated pipelines running comparisons at scales and speeds that no team of astronomers could match. This is already happening. And what those systems are flagging is already surprising the scientists who built them. According to informed sources in the astrophysics community, the commissioning data from Rubin's early optimization phase has already produced a number of unexplained transients, objects that appeared, changed in brightness in ways that did not fit standard templates, and faded, whose classification remains open. Some of these may turn out to be known phenomena observed at unusual angles or distances. Some may be instrumental artifacts that careful calibration will resolve, but some may be genuinely new, not new versions of things we know, new categories of things, phenomena that the universe has been producing for billions of years in the parts of the sky that previous telescopes were not fast enough, or sensitive enough, or wide field enough to catch. Here is what the real story is, stripped to its essential truth. The Vera C. Rubin Observatory is not a telescope that answers questions. It is a machine that exposes them. It is built to map the universe at a resolution so fine that every crack in our understanding of it becomes visible, and the cracks are already showing. Dark energy may not be constant. The Hubble tension is real and unexplained. The large-scale structure of the universe does not perfectly match what the models predict. Planet 9 may be out there, or it may not be, and either answer is significant. Interstellar objects like the recently detected 3I Atlas pass through our solar system at speeds and trajectories that hint at origins we cannot yet trace. And somewhere in the 7 million alerts that Rubin will fire tonight, and tomorrow night, and every night for the next 10 years, there may be something that none of the models anticipated. Something that will require not a refinement of what we know, but a complete reconsideration of it. We have been told that the universe is 8 billion years old. We have been told that it is made mostly of things we cannot see. We have been told that it is expanding, accelerating, cooling, growing darker and more diffuse with every passing billion years. And we have built those conclusions on data collected by instruments that were extraordinary for their time but limited in ways we are only now beginning to quantify. The Vera C. Rubin Observatory is the first instrument in human history powerful enough to test all of those conclusions simultaneously at a scale that leaves no room for comfortable ambiguity. It is not looking for something specific. It is looking for everything. And in 10 years, we will either know that our model of the cosmos was essentially correct, or we will know that what we thought was the universe was just the part of it we could afford to see. The question that nobody is fully prepared to answer is this. When a machine this powerful looks at everything and sees something that nothing in our physics explains, what do we do next? What does it mean for our understanding of space, of time, of gravity, of the fundamental forces that hold reality together? And what does it say about the century of science we built on the assumption that the universe was mostly empty, mostly knowable, mostly already mapped? On a mountain in Chile, under skies so dark and dry that the stars seem close enough to touch, the Vera C. Rubin Observatory is pointing its 3-ton camera at the southern sky and firing 7 million alerts into the global network of science. And somewhere in that flood of data, something is waiting to be found that will change the answer to the oldest question humanity has ever asked. We just don't know what it is yet. And that is the most honest, most terrifying, most extraordinary sentence in all of science right now.